Yeah, good afternoon, everyone. I want to welcome you to another week on another chapter. And of course, we are counting down to final exam. And of course, the final exam is going to be written in person. Of course, you already know the date. The midterm two results will be out on Wednesday. Okay, so today we're starting a new chapter that we call Introduction to Linear Models. Before now, we've actually focused on a random variable. And, we actually take a random sample of data from the population. And the reason why we do that, maybe we want to figure out the true value of a parameter. And because of that, we normally have suggestions about what the estimator is going to be. And of course, in the process of searching for estimator, the idea of, factorization theorem was used because we actually want to get sufficient statistic. And we believe, using the Rao-Blackwell theorem, we're able to, search for a unique minimal variance unbiased estimator that we believe is a function of sufficient statistic, and in a situation where the function of sufficient statistic is complicated, of course, we actually use two well-known method of estimation that we call the method of moment and the method of maximum likelihood. And of course, all of that, we have an assumption that the response variable, the mean of the response variable, we actually give a constant. I'm going to say that again. When we're dealing with the unbiasedness property of an estimator, we normally have a situation where at the end of the day, we're going to get the expectation of a particular estimator will be equal to a constant. But I want to tell you that in some situations, and I'm going to say in most situations, the expectation of the response variable is actually is going to be a function of another set of variables. I'm going to say that again. The expectation of a random variable is going to be a function of another set of variables. So which means it may not be realistic to say that the expectation of y is going to be a constant. And what we want to do today is to unravel situation where the expectation of the response variable is going to be expressed as a function of some variables that we call independent variables. Okay, and that is why I think I'm going to give you an example. For instance, if I want to talk about the mean stopping distance for a particular type of automobile, you want to figure out on average, okay, how a vehicle that is in motion is going to stop. That would depend on the speed. Does that make sense? So the average stopping distance now for an automobile will depend on the speed that automobile is actually driving. And that is one of the reasons to say that we're actually going to have a situation whereby the response variable will be related to one or more variables. Like the one I'm trying to show you now, I actually want to talk about the income of a person. If you want to go by all what we've been doing before now, we've only been looking at just response variable only. We believe it doesn't depend on any other variable. That has been our focus. But right now, we want to be able to investigate the role played by some variables on the dependent variable. If Y is income of a person, then that is going to be related to the years of education. Okay. And not only that, it could be related to more than one variable. Okay. Now, if we want to do this, we need a linear modus to be able to achieve that. And we actually call that area, we call it regression. You know, regression is a way to relate a particular response variable that we're going to call Y to some independent variable. Now, if you take a look at this, if I really want to investigate that relationship, then I need a function. I need a function that will give us that relationship. I'm going to say that again. We are searching for a function, okay, that will actually give us that relationship. And let me tell you, maybe you might have come across some, when we talk about models, we got deterministic model, we got a probabilistic model. And which one are we going to use? What do I mean by deterministic model? You know, deterministic model is a model that we assume that will give exact representation of reality. Okay? A model that we assume that will give an exact representation of nature. We know we can find some of those models in physics. I remember F equal to ma, force equal mass times the acceleration. We do have such models, but I want to say in a real stochastic world, okay, we need probabilistic model. In statistics, we use probabilistic model because we believe that whatever our model may not give an exact picture of reality, there's always going to be an error. I told you in the first day, model is not the same as reality. Model is an exact, it's an approximate, it's going to give approximate reality. And because of that, having an error in our model, okay, is doing a lot of job. Error in our model will enable us to investigate how valid is our model. Does that make sense? So having error in a model, okay, will enable us to investigate the validity of that particular model, because the error that I'm talking about is going to be the distance between the model and exact picture of reality. Now, when you take a look at what I'm actually displaying right now, give me 1 second. When you take a look at this guy now, okay, we're actually relating y is approximately g of x. Okay, now we're trying to say that g of x, a function of x, is what we need. It's going to be a relationship here. It's what we actually need to know, okay, between y and x, between the response variable and the dependent variable. The y here is going to be called response variable. We also call it dependent variable. Yx will be called independent variable. We also call them predictors. We also call them explanatory variables. Okay, and when you take a look at when I have a situation, okay, give me 1 second. When you take a look at what I have, okay, when you take a look at this guy, y equal g of x plus the error, y equal g of x plus the error, we have incorporated, okay, a random component into the model. Initially, y equal to g of x is a deterministic. We don't use a deterministic model in a stochastic environment. So we introduce the error here, which is called the random part. And of course, the error that is introduced, assumptions will revolve around the error. And if I want to know how good is the model, then I need to investigate whether assumption underlying the use of the model hold. A model is as good as assumption putting into a model. And you know what? By the time I take the expectation of both sides, then I'm going to have the expectation of y to be equal to g of s, because the expectation of the error is assumed to be 0. Let me tell you this, error is not equal to 0, but on average, it is 0. That's what we mean. Does that make sense? So when the expectation of error equal to 0, okay, when the expectation of error equal to 0, then we can actually have a reasonable estimate or prediction or whatever that we want, seeking the model. I told you the other time. Now, I'm going to go into an example now. You actually have some set of individuals and you want to look at the relationship between income and the years of education. We want to see maybe does that mean if I go to college and if I earn maybe qualification, does my salary, I want to see the effect that is going to have on my income. And for us to be able to see, we actually take a sample of individuals, any income, okay, maybe the income here is in thousands of dollars. It could be, the first individual or after 12 years of education. I want to believe the 12 years of education is going to be like high school, right? Up to high school, right? And that person has $38,000, 16 years, 120, and so on like that, okay? So now, if we actually want to have a sense of the relationship, which means here, we needed to derive a function, a g of x, that will relate the response variable y, to the independent variable x. Then I can do a scatter plot, where I'm going to, plot, the response variable against the independent variable, as you can see. Okay, so the nature of the relationship displayed in the scatter plot will give you a sense of what the function is going to be. Like before now in mathematics, you've learned a linear function, quadratic function, cubic function, exponential. There are different kind of function around. But if you want to have a good start here, I need you to start by having a diagrammatical plotting of y against x. And that's what you see now. Now, take a look at this now. You can see it's looking like a curve, okay? And you're actually going to see some dotted line in red, some dotted point that you see it in red. That is why it is called a scatter plot, okay? Even though I'm going to draw something that look like a straight line, if I'm using a straight line relationship, it is not going to be all the points that will be on the straight line. There's going to be deviation, okay? Now, if all the points are on the straight line, then you are assuming, your model is perfect. Okay, you're trying to tell the world your model will give exact reality. I want to tell you, your model will not give exact reality, and that is the reason why in statistics we have acknowledged the fact that model is not equal to reality by incorporating a random component into our model. And if I want to know whether, how valid is my model, how reliable is my model, of course, all what I need to do is to investigate assumptions. Assumptions revolve around the error in the model. Okay, so I want to go into application now of regression analysis. And I just told you right now, regression analysis allow us to regress, the response variable on one or more independent variable. I remember what I did in one of my projects when I was doing bachelor program in Africa. I actually work trying to look at the effect of exchange rate, inflation rate, and consumer price index on the GDP of Nigeria. You know, when I'm trying to look at that, it means I'm relating a response variable to 3 independent variables. And not only that, the module I'm actually going to use, we have an error in it. And that very error is going to tell us any other effect, you know, any other factor that could affect the response variable that my module do not capture at the moment. Okay. And of course, we expect on average those effects to be 0. Otherwise, if they are not significantly different from 0, then we're actually going to run into what I call a module misspecification, because it is not good for you to have a missing value, a missing variable that is very, very important in your model. Now, take a look at now, regression analysis is very useful in uncovering the effect of uncertain factors on the response variable. Here now, when you take a look at what I'm trying to display now, income, approximately equal G of, which means we want to look at the effect of years of education, experience, gender, or income. But let me tell you this. Maybe the very first thing, the primary variable of interest could be education. Maybe I want to look at the effect of education, but I need to incorporate something that I'm going to call covariate that could also have effect on income, like experience and gender, which means what we call this in statistics is that we are actually trying to control for the effect of other variables. Because if you don't control for the effect of other variables, you're actually going to mislead. Okay, now take a look at that. Now, that's why I said, after controlling education, experience, does one gender, earn more than the other on average? Let me tell you this. If you want to base it on what we've done before in this class, we've done difference of means in 2 population, right? Do you know, if I only want to, the difference of means in 2 population will not take into consideration other factors that have effect. Like if we want to go by what we've done before, here we can compare the average salary of male and female. Okay, comparing average salary of male and female, you can go by way of 2 sample t-tests, but that will not, that will not enable you to also control for the effect of years of education and experience. And that is the reason here, maybe the primary variable of interest is gender. Maybe I want to look at the effect of gender on income. Looking at the effect of gender on income is to see whether there's a significant difference between income earned by female and male. But along the line, you realize that there are some other potential variables that need to be controlled. Okay, and what are these variables? The variables that need to be controlled are those ones that we actually feel that they have also likely to have effect on the income, which is education, years of education and experience. In a situation where you only test for the effect of gender on income, and if there exists some other variable as well that need to be incorporated into your model, then you're actually going to mislead. And you can see that said after controlling for that. And because of that, it actually means we're going to have 2 forms of model. Take a look at this. Why do I say 1 and 0? Because the gender is categorical variable that we can label as 1 and 0. Okay, if you take a look at this now, I'm comparing the income of male and female, putting into consideration their years of education and experience. Who doesn't understand what I circled? Who doesn't understand that? It's like I'm having 2 different functions. One function is actually for female and the other one is for male, and in the 2 of them, and I'm controlling for their years of education and experience, because the years, so it makes sense to include years of education and experience as a determinant factor for income. Even though my primary variable of interest here is actually gender. And that was why I labeled 1 as, 1 and 0. Okay, now we're actually talking about, the significance of, regression analysis. Okay, and another is it will enable us to make a reasonable prediction. Okay, like what is the essence? Okay, predicting the value of a response variable given the values of predictors. Okay, so I need to first study relationship. When relationship exists and some other assumption hold, I can use the model to make a prediction. If I know somebody years of education, I know somebody years of experience, and whether it's a male or female, and I can actually come out with a reasonable prediction for the income. Okay, and of course I gave an example right here, predicting life expectancy. The life expectancy actually depend on age, the gender, the pre-existing condition, and so on like that. There could be other factors as well. And of course, what about the final grade for this class? Of course, the final grade will depend on what was your grade in midterm 1, in midterm 2, the homework grade. Okay, so take a look at all of that. But let me tell you this. There's also going to be error. Because the error, there are some other things, apart from all this grade, there's some other things you do. What about your intelligent quotient? What about whether you study hard or not? We are actually assuming that the effects of other variable that is not going to show in the model, we are assuming they have a very negligible effect. Very small effect, very negligible effect is what we mean by expectation of the error equal to 0. I need you to see that that very error represents any other variable that could have effect on the response, but our model don't capture that at the moment. Does that make sense? Okay. Now, going into parametric model now. So what we're actually seeking for, we're actually seeking for this guy here, okay? And that can be a complicated, okay? Complicated in the sense that it could be a polynomial of degree 1, degree 2, degree 3. It could be exponential function. It could be any form of function at all, okay? And in general, I said there is no hope of finding the exact form of that based on a finite amount of data. Let me tell you this. In research, we always take sample. Our data is finite. Okay, if I want to get a function that will relate the response variable to independent variable, there's no way I will get an exact function. Not getting an exact function means you are not getting a perfect model, which means your function is going to be estimate. Does that make sense? Okay, and that is what we actually mean here. And let me tell you this. That function now would be a function of parameter theta. Okay, would be a function of parameter theta. And let me tell you this. Okay, if I want to start by showing you the parameter theta, in the case of when I'm assuming a straight line, take a look at this guy. When I'm assuming a straight line, that parameter theta now is going to be beta naught and beta 1. The beta naught is a regression constant in mathematics. They call that intercept, while the beta 1 in mathematicians call that slope. Okay, we call that slope. Okay, so when you take a look at the model here, okay, you're actually going to see this is a graphical representation of that particular model. But I just wanted to, this is a true function. Why is it a true function? Because I've not had an error. There's no error. Does that make sense? You can say I just have G of that. Okay, this is deterministic for now. It is only where we incorporate, don't forget, the word we're looking for, the true function we're looking for, okay, it's actually deterministic in nature, but we can't get it. And that is why we need to estimate that, right? Now, another function could be quadratic in nature, okay? And how am I going to know the shape? I'm actually going to know the shape by trying to start, by generating a scatter plot. That will give me the sense of what function I'm actually going to specify. When you are using the idea of statistics, what we normally do, we start with the specification of our model. Whenever we want to figure out a kind of a model that will characterize relationship between variables, if we want to have the idea of a model, we're going to specify parts of preliminary investigation is to construct a scatter plot. Okay, now, and after you've done that, you got different kind of models. I'm just trying to show you the few aspects. Okay, I'm just trying to show you a few. Okay, now there's another type of model. There's an exponential model. Okay, we got different kind of functions. Okay, and of course, the reason why I'm trying to show the corresponding graphical representation is for you to be able to recognize the name of the function after you have succeeded in constructing a scatter plot. Because I know your scatter plot is going to show a particular shape. And I said, assuming that the parametric model is reasonably close to the truth, the estimation of that become estimation of theta. So which means here, we're still going to be estimating function the same way we were estimating parameter before now. We are estimating relationship. Why are we estimating relationship? Because we can never get an exact relationship anywhere in the world because of the fact we're using a finite data. Okay, now, what are the steps for regression? Number one, I told you, you need to choose a parametric model. Am I going to choose linear? Am I going to choose quadratic? Am I going to choose exponential? I think what is going to guide you in choosing a reasonable parametric model is when you have constructed your scatter plots. Does that make sense? That's going to give you the sense of that. And you know what? And I said, ideally, the model should be complex enough so that it can capture potentially complicated relationship between the variables under investigation. And it should also be simple enough so that theta can be accurately estimated. Because let me tell you this, if your model is not simple, you are likely going to experience difficulty in estimating parameter. Okay. Now, in estimation of theta, then after you have specified your model, then what is the next thing? Every model comprises of parameters. Then the next thing is to estimate parameter. That's what I call the estimation of parameter theta. Okay. Now, the next thing that I want to show now is I want to first start with a simple linear relationship. Why is it called simple linear relationship? Because I only want to relate response variable y to only one independent variable. Okay, and that is why when I have given a response variable y and a single independent variable x, that's why it is called simple. But if I have more than one independent variable s, that is going to be multiple linear regression. Now, in the specification, I told you if we want to start, we're actually going to start with the specification of the model. After constructing a scatter plot and we saw a straight line, right? Then this is the model that we're actually going to specify. When we take a look at the model here, we've added error, right? Take a look at this guy. You can see, which means I'm going to tell you the takeaway now. If you take a look at this side, that's a deterministic part. This is the random part, a statistical model. So which means y is contaminated. The response variable y is contaminated with the error. The response variable y, the model here is actually, we specified it in a way, we got a combination of a deterministic part and the random part. The random part is the error, and when I take the expectation, because you know why? This variable y is random. It varies. That is going to have a distribution. We expect the distribution of the response variable to be normal. Does that make sense? You remember we've been talking about normal. So we expect the distribution of the response variable to be normal. And if the distribution of the response variable is normal, then the distribution of the error is also going to be normal. And when the distribution of error is normal, then we can actually say the expected value of the error is going to be equal to 0. That is looking like a standard normal distribution. You remember in a standard normal distribution, the expected value of z is going to be equal to 0. Take a look at that. Now that's going to be a simple linear regression model. Take a look at that. And, we can also have a situation, where we got a non-linear part. The connection between this and the non-linear part is just going to be the way x is specified. Now, when you come here now, give me 1 second. If you come here now, you're actually going to see we are no longer having x, but we're having x squared. That's quadratic regression. Okay, we could have x raised to power 3. Take a look at this. We're no longer having s, it's the cos s. Here we are no longer having s, it's the natural log of x. Okay, now, and that was why I said here s squared cos of s log of s as a new variable, as new independent variable. Take a look at that. So we can actually have, different scenarios, different situations where that is going to be appropriate. Okay. I'm actually going to move to a situation where we got, when we took a look at all this, we're still focusing on one independent variable. Go ahead. Which one is it? Which one? Oh, you mean the intercept, the beta naught and the beta 1. So how do we differentiate between them? Oh, you mean the error here? Okay. Are you talking about this guy, the error there? So how do you differentiate between which one and which one? Yeah, actually what happened is the way we normally do it. If you take a look at this guy, let's say I want to predict y, then the beta naught and the beta 1 become an estimate. This guy is going to be having a cap. This is going to have a cap. When it has a cap, that's an estimator. When this has a cap, does that make sense? Now, in that situation where you take a look at this now, why here, in a deterministic form, the beta naught and the beta 1 are the population parameters. Why, when you include the error now, okay, including the error means, because you want to work on sample of data, not the overall, then your beta naught and the beta 1, they will be called estimates of the linear regression parameters. Does that make sense? So the beta naught here is just going to be population regression constants. But the one or the other one is going to be called estimates of the population regression constants. Does that make sense now? So that is what that means. Okay, now I'm going to clean up this guy now. Go ahead. Well, does that mean which one is the only random variable we have? Yeah, the only random variable here is assumption is on assumption is y, the response. We normally believe that x is fixed. So, and that's a good question. What make y to be random? Because y also depends on the error. If you look at the way the model is specified, y is a function of the error. And one of the assumptions is that there shouldn't be any relationship between X and the error. You know, when I say X and the error, there shouldn't be any relationship. For instance, if I'm talking about, if I'm looking at the effect of years of education on income, assumption is that if I'm only using years of education as independent, there shouldn't be any relationship between years of education and something that I did not mention that have effects on the income. Does that make sense? So which make X to be what? Fixed, not subject to variation, but the only random variable is the Y, is the response. Does that make sense? And that was why you can say that we're going to talk about expectation of Y. We're not going to talk about expectation of X here, because we assume S is constant, and even expectation of a constant, say constant. Okay, now I want to go into the multiple aspects, situation where, just like what I told you I work on in my project, where I look at the effect of exchange rate, consumer price index, inflation rate on the GDP. Now we take a look at this guy now. Okay, we got more than, this is like having P numbers of independent variable. Situation where number of independent variable is more than one, and you're assuming a straight line relationship, that will be called a multiple. The model you're going to use is going to be multiple linear regression model. But in this case now, the numbers of parameters is going to be huge, because you're going to have a P plus 1 numbers of parameter. P plus 1, plus 1, that one is the intercept, beta naught. Does that make sense? Now, and that was why I said multiple means greater or equal to predator. I think I'm just going to say more than one predator, not even two. From two predators is multiple. Does that make sense? And we can also have a situation whereby each of them could be squared, just like the same way we have in the simple linear regression. Okay, and that's what you see here. There's something I call polynomial. In general form, there's something that we call polynomial regression. You've heard about polynomial function. This guy here is when the degree of the polynomial here is P. Does that make sense? Okay, we can talk about polynomial regression model. And if you take a look at another example here, we can have a situation whereby two variables will interact, like independent variable interacting. Okay, interaction, we're going to call that interaction model. And we have a way to test whether interaction is going to be significant or not. Okay, all what I'm just trying to show you here, just to show you different kinds of models that we have. Okay, now, when we have statistical model, we're actually going to have them in terms of parameters. The way they're going to be expressed, they're going to be expressed in terms of parameters. And after specifying them, we need to estimate them, estimating the parameters. And after estimating the parameters, if everything is good, then we need a way to interpret the regression coefficient. Now, for instance, if I have more than one independent variable, maybe I'm talking about looking at the effect of years of education and years of experience, or maybe probably I'm looking at the effect of that on income. And take a look at this. Maybe at the end of the day, when I use my software and I arrive at this, which means here my beta naught is 20, estimate of beta naught is 20, estimate of beta 1 is 0.7, estimate of beta 2 is 1.2, and maybe I want to interpret estimate of beta naught. What estimate of beta naught is going to tell me, then you need to quickly go back to high school when you were working on the y-intercept. What do we call y-intercept? The y-intercept is the values of y when s equal to 0. Now, that 20, it means the average income is going to be 20 when the years of experience is 0 and years of education is 0. Does that make sense? That is what that 20 means. On average, okay, on average, the income is going to be 20 when the experience is 0 and education is 0. Now, what if I want to interpret 0.7 on the experience? If I want to interpret the 0.7 on the experience, I need to first tell the world after controlling for the years of education. I have to mention that. After controlling for years of education, okay, for any increase, a unit increase in experience will lead to, on average, will lead to a 0.7 increase in income. Does that make sense? That's what it means. If I want to interpret the 1.2 on the education, on the other hand, if I want to interpret 1.2 on the education, on the other hand, I'm going to say after controlling for experience. I have to mention that. Controlling for experience means you're adjusting for experience, or in another word, you're going to say holding experience at constant. Okay, then a unit increase in the years of education on average will lead to 1.2 increase in income. That's what it means. Because I got a plus, that was why I was saying increase. If it is a negative, I'm actually going to say decrease. Does that make sense? That is how that is done. Okay, now, is there anyone want to ask a question on how the interpretation is made? Okay, now let's look at the type of data set you're actually going to have. You know, you're going to have data set on income, Y, then experience, education, gender. Then I need you to take a look at what you see on that gender. You're going to see 0, 1, 1, because that is categorical to levels of gender. Okay, one is going to be 0, we're going to call 1 0, the other one 1. And let me tell you, the one we call 1, that doesn't mean it has a numerical advantage against the other one. It's just for numbering. Does that make sense? Okay, so that is the way the data set is actually going to look like. And based on this data set, go ahead. Oh, you mean whether on the interaction where we're going to use the dummy variable, right? Yeah, because at times we may, the idea of the interaction is going to, let me tell you the meaning of interaction practically. You know, one of the variable here is gender, right? It's categorical, right? We may want to develop a model, okay, where that will connect, you know, uh, uh, maybe I wanted to generate 2 different models. One is going to go based on male, and the other one is going to be based on female. And in each model, okay, you'll be able to see how experience and education relate to income in each class. Okay, so with that, I may need to incorporate interaction, and it could be, I can look at the interaction between experience and gender. I can look at interaction between education and gender. Okay, so interaction comes in, in different ways. At times, when 2 variables interact, then what it's trying to tell us is that the effect, for instance, let's say, I just want to assume this. If experience and education interact in a model, it means the behavior of experience on income is not consistent. It's not consistent. It said that the behavior of experience, the effect of experience on income depends on education. That is what the word interaction means. That is if interaction is significant. Does that make sense? If the interaction is not significant, then you expect the factor to have a consistent behavior or consistent effect on the response. So in a situation where interaction is significant, then it means, just like the example I gave right now about experience and education, okay, it means the behavior, the effect of education on income depends on another variable. And that is only if and only if the interaction is significant. Those are the kind of stuff we can investigate. Have I answered your question? Okay. Now I think I have time to listen to questions. Is there any question about this? Is there any question? We're not going to have an in-person teaching on Wednesday. We're actually going to meet via Zoom, because I know some of you will travel for Thanksgiving. And like I said, I'm in the process of I'm grading right now, and I'm hoping by Wednesday you're actually going to see your results. So while you travel for Thanksgiving, make sure you stay safe. Okay. Now, like I said, on Wednesday, the lecture is going to be on Zoom. You just need to join the class Zoom, the same class time, but there's not going to be lecture on Friday. Okay. So after Wednesday meeting on the Zoom, our next meeting is going to be on Monday. Make sure you all stay safe and have a lovely day. Bye for now, everyone.